You make me smile like the sun, fall out of bed, sing like a bird, dizzy in my head, spin like a record, crazy on a Sunday night. You make me dance like a fool, forget how to breathe, shine like gold, buzz like a bee, just a thought.
Good afternoon, everybody. Hope you're having a fantastic day. Little Uncle Cracker there for you. Hope everybody's day is going amazingly, swimmingly so far. I have a couple of things that we need to talk about today. It's a monumentous day here, monumental day. Today we're going to be talking about the formal definition of a derivative. Now, day before yesterday, we talked about the definition of a derivative, like what a derivative was. And if you remember what we did in class, we talked about the derivative as x approached some value c. And we actually had a value for c. So if you have a value for c, it's fantastic because you can just use that value for c. And then you can go about do the definition of the derivative and all that stuff. But the formal definition of a derivative has to take away that c. We have to approach this as, what if we don't know what c is? You know what I mean? What if we don't know c? What if it's just x f of x and some other point? So if you look at this graph here, we've got a graph of a function here. And we've got a point, x comma f of x. So this is your x value here. This is your y value, f of x is your y value here. And then we've got q. And the difference between them is some kind of delta x. Some change in x. Remember, delta means change. So it's some change in x. Well, if that's the case, think about this for a moment here. It says down here, it says to find the derivative, let's examine the following. Define the coordinates of q. Define the coordinates of q. If I wanted to write a set of coordinates for q, I'd take x, add delta x, and I'd be at this x value, right? If I take where I'm at with x here, add delta x, and I'll be at this x. So I'm going to write that just like I said, x plus delta x. That's the x value. So then the function would be f of x plus delta x. Now please don't let the notation here fool you. All we're doing is taking this x value right here, that's where our x is, and we're adding to it delta x, this distance, delta x, and we're at this distance, which is x plus delta x. See, to be a formal definition, you have to take away the possibility that you know what the constant is, that you know what the value of c is. What if we don't know? So this has to work. So to define the coordinates of q, just like we wrote, it's x plus delta x, f and x plus delta x. So those are the coordinates of q. So using that, let's find the slope of the secant line for PQ. Remember, slope of the secant line is what goes from P to Q, y2 minus y1 over x2 minus x1. So it's going to be f of x plus delta x minus f of x all over x plus delta x minus x, y2 minus y1 over x2 minus x1. It's the formula for slope is all it is. y2 minus y1 over x2 minus x1. So now let's think about what actually happens if we were to do the limit again. What happens as delta x approaches 0? What happens as the change in x gets smaller and smaller and smaller? So what happens as q gets closer and closer and closer to p? For that, we have the formal definition of a derivative. That's what's in the box here. The derivative f prime of x of function f of x is the function defined by f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. That's the change in x, right? Now what about this? This delta x. Up here it was x plus delta x minus x. Now it's just delta x. Where in the world did the x and the x and the... Oh, wait. It's an x and it's a negative x, isn't it? Those would just go away. So wouldn't this simplify to just delta x on the bottom? That's where that comes from. For every x such that the limit exists. Meaning no asymptotes where you approach two different things, blah, blah, blah. All right? No holes. Well, no removable discontinuities in it. Or no piecewise functions where you're approaching two different things. The limit's got to exist here. So the derivative is this function right here. And what this does, this is the formal definition of a derivative because it takes away the possibility that you know C, that you know what C is. What if you don't know what C is? Okay. So there's a couple of things that I wanted to go over here. Down at the bottom it says derivative notation. That's on the next side of the page actually. Derivative notation. It starts off with f prime of x is the derivative of f of x. F prime of x is the derivative of f of x. This is what we use for function notation. If instead of using y, if we're using f of x, this is the way we write it. F prime of x. If we are using y instead of f of x, then we use dy over dx. It's the derivative of y with respect to x. These two things mean the exact same thing. One is just using function notation. The other is using y equals notation. And then finally here you've got f prime of x, which is, this is the formal definition, is what we just learned on the other page. As delta x goes to 0, what's going to happen in here? Okay? So because of what we've been doing the past couple of days, you already know how to use the limit. So let's actually figure out what the formula for the derivative would actually look like. So on the first one here, it says find the derivative of f of x equals x squared plus 2x. Now, since we're actually finding the derivative, remember that this is where a lot of people are going to want to use those shortcuts that we haven't learned yet. Just please back off for now. I'll teach those to you later. If I'm specifically asked to use the formal definition, using the formal definition, I must use this guy. Because what's the whole point of this class? It's to get credit on an AP exam. That way you can get credit for college, also to learn a little bit of calculus while you're doing it. All right? So if it says to use the formal definition, I actually want to see the formal definition. So let's write our points here. We've got a couple of points. We've got first off, x comma f of x, right? And then we've got x plus delta x. And the way that this is going to look is if we actually plug in an x plus delta x here and an x plus delta x here, what would it look like? So I'm going to go ahead and do that. I'm going to say it's something squared plus 2 times something, right? Open up a parentheses wherever you've got an x in the original function and plug in x plus delta x. That's what f of x plus delta x looks like. That's what this guy right here looks like, f of x plus delta x. Plug in x plus delta x. Bing. Wherever you've got an x. Now before we go any farther, let's actually figure out what this guy becomes. X plus delta x squared, let me do this over here, is x plus delta x times x plus delta x, right? X squared. You've got x delta x, that's 2x delta x, and then delta x squared, right? So this is going to be x squared plus 2x delta x plus delta x squared plus 2 times x plus 2 times delta x. Please don't get confused at all the deltas that are thrown in there. You know that a delta is just a placeholder for some change that you don't know. Nothing different than a variable. That wouldn't be any different if I had a y there, right? So let's actually figure out what this is going to be then. F prime of x is equal to the limit as delta x goes to 0 of gonna be a pretty big one. Let me throw these in some brackets here, make these look pretty. It's f of x plus delta x, right? Let me go up here. F of x plus delta x, which is this guy right here, x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x. That's f of x plus delta x minus f of x. That's x squared plus 2x. All over delta x. Yay! Let's figure out what happens here. So start off by distributing your negative. This will be negative x squared and negative 2x. So your positive x squared up here, negative x squared here, those will go away. You've got a negative 2x and a 2x. Those will go away. Let's see what we're left with. F prime of x is the limit as delta x approaches 0 of 2x delta x plus delta x squared plus 2 delta x. Just bring down those three terms you're left over with. All over delta x. Now here's what's cool about this. Notice, what do they all have in common? They've all got a delta x in common, right? So think about this here. If I pulled out that delta x out of here, let's say I pull out delta x. What's that going to leave me with? That'll be 2x plus delta x, because it was delta x squared, plus 2 divided by delta x, and what do you know? Ba-da-da. Okay, so let's keep going here. Let's figure out what this is. So f prime of x is the limit as delta x goes to 0 of 2x plus delta x plus 2. I don't see anything else I could simplify there. So what did we say in our limit was happening to delta x? See, originally we were going to 0. We had to get rid of this guy somehow because we can't divide by 0. But now we're not dividing by 0. So can we just say that delta x goes to 0 and take this guy to go to 0? So what are you left with? F prime of x is 2x plus 2. This is me applying the limit, so I can get rid of the limit, and I'm left with 2x plus 2. That's crazy. And I'm going to stop this here. I'm going to show you the graph when we get into class.